Okay, so we're looking good on the recording, and here's what we were talking about last time. We were talking about an application of level sets to creating topographical maps, right? And we talked about contour lines being these curves like this, and using these curves, you can kind of, in some sense, get somewhat of an idea about what the shape of the land is that it's describing. And here you can kind of sort of see that there's a mountain, or, a hill or something to that effect happening there. So this can be helpful in various situations. We are talked about this scenario of if you wanted to go from here to the top of the mountain, you don't just go straight up. Correction, I would not just go straight up like that. That looks like a lot of work and I don't want to. I would much rather go around like this where I'm not crossing any contour lines that are really close together, right? And that spaces out the elevation gain, one way to say it, and thus it's not as steep. And it's a longer hike, but it's a more sort of like palatable thing. So I want to show you all a real-world example of this. So I swiped this off of Google Maps, and this, in case you're curious, is a point of interest. This is called Mount Evans. It is the highest paved road in the continental U.S., and it's pretty neat, by the way. I've been up there many times, and when you get up to where the road ends, you're over 14,000 feet, and zero effort expended, at least by you. Your car had to work pretty hard to get there, but it's a really interesting drive. So let me talk though about the shape of the road. Right, so it's kind of a super zigzaggy road. Why wouldn't they just go for example, from here, if you want to get to the parking lot, why wouldn't you just go like that? Well, you can see on the map, look how close together these contour lines are as you go in that direction. And so that would be a extremely steep road. Most cars would just not be capable of the amount of power that it would take to actually drive up something that steep. So look at what they do instead. Notice that the road along in here, for example, is not exactly following contour lines, but to a large degree. I mean, they're not cutting through a lot of contour lines very quickly. They're mostly following contour lines, and then maybe just kind of cutting upward just a little bit at a time. And now, in some situations, of course, that'll get you into trouble. And so, for example, if you're here trying to follow the contour lines, eventually you're just going the wrong direction. And so you then have to do cut back, and then cut back again, and then cut back again. And they call these switchbacks. That's just a term that they get for it. But notice everywhere along the road, wherever you are on this road, you're not cutting straight across contour lines in most places. You're mostly kind of following and then just maybe ever so slightly aiming uphill from level. So this makes it so that most cars can do it. So this is another piece of information that you can get off of contour lines, aka level sets. Okay. All right, and then side note, just for fun, this is a harrowing road to drive on. There are no guardrails. The road is in poor condition, and if you were to fall off the road, let's say there, again, no guardrails, right? The road could crumble underneath your tires, or so it would seem, given the shape of the road, and notice how far you fall. And that's just before you get down to the next piece of road, and you might keep going down below that, of course. And so it's many hundreds of feet and extremely dangerous. And then add to that the fact that when you're at 14,000 feet, when the day before you had been at 300 feet elevation, aka Duke elevation, your brain does not work right because it's 14,000 feet. The air is extremely thin up there. And so not only is there no guardrails, poor condition roads, but your brain is really not working at full functionality, nor are those of the other people on the road. And so you got to worry about, is some crazy guy going to run me off the road? And anyway, it's very harrowing, but it's a very exciting drive. And the view when you get up to the top is just insane. Okay. All right. So enough of that. All right. Moving along. So there's a nice relationship between graphs and level sets. However, got to emphasize, and I've said this before, I'm sure I'll say it again, They're different things. A graph is a very different thing from a level set. So you can see the difference right here. A graph is where you set the function equal to a new variable, like z in this case. A level set is where you set the function equal to a constant. And these are very different things. We've said a bunch about that. But notice this. Having set the function equal to a new variable, if you then set the variable equal to a constant, well, altogether then, altogether, f equals z, z equals a constant. Altogether, you get f equals a constant. Just like the level sets. F equals a constant. So what that means is that this sort of two-step process of taking the graph and then setting z equal to a constant, namely taking horizontal cross-sections. If you think about it, z equals a constant is a horizontal cross-section, right? A horizontal cross-section of the graph gives you the same equation as that of a level set. And so you'll notice I have that written down here, that level sets are horizontal cross-sections of graphs. And I think that rolls off the tongue very nicely. It's a very strong relationship to be aware of between graphs and level sets. By the way, that is a motivation for the term level set. It's because these horizontal cross-sections are, you might say, level. They're horizontal, perfectly horizontal. Okay, so an example. Here is a function, and here we're taking the level set, setting it equal to a constant. We already studied that. That gives you circles. Right? Actually, let me go ahead and trace those out. There we go. There's our level curves. On the other hand, if you take a graph by setting it equal to z, and then a horizontal cross-section by setting z equal to c, right? Let's draw pictures of those. This graph we've talked about previously is a bowl, kind of like that. By the way, I'm going to give you a more full understanding of where this picture comes from, claiming that x squared plus y squared equals z is a bowl. I'm going to talk about that in great detail in a few minutes. So there's the graph, and here's taking horizontal cross-sections of the graph. And notice, when you take these orange horizontal cross-sections of this green graph, notice that you get these exact same circles that are the level sets. So this is just a, in action, real-world scenario of what we just talked about. And I'm just trying to get this thing out of my way here. Oh, gosh. Let's see if I can... There we go. Okay. Okay, what do you think? Everybody happy with that? Okay. So, so we've talked about now various different constructions for how to understand functions, or to say it a little bit more broadly, different connections between functions and pictures. So let's talk about them real quick. We've talked about the graph construction. You give me a function, I give you a picture by way of a certain construction. The level set construction. You give me a function, I give you a picture. It's a different picture because it's a different construction. And then let's not forget about parameterizations. We kind of think of parameterizations the other direction, right? But if you give me a curve, then parameterizing the curve results in a function. So again, it's a connection between functions and pictures, and okay, maybe you think of it in the other direction, but whatever. It's still a connection between functions and pictures. So we have now several of them. So if I give you a curve, for example, a line, and let's look at this line right here, this line L, with this equation, and I ask what function are we looking at there, there's actually a bunch of different answers, depending on, well, in what sense? What is the connection between algebra and geometry that you're interested in, and why? Right? So let's think about the different versions there are of this. I claim that we can think of this as being a graph. In particular, it is a graph of this function. And you don't immediately see where that comes from. I'll explain where it comes from momentarily, but first let me persuade you that its graph is what I claim it is. Notice that if I take this function of just x, I'm going to set its values equal to a new variable, y, because after all, we're talking about doing its graph. And this is what a graph is. Right? We're taking a graph of a function, you set the values equal to a new variable. Notice that the result is an equation that is equivalent to the original equation for the line. So, in fact, then, the graph of this function gives me the same line. So, what function are we looking at here? Well, in the sense of being a graph, this line is the graph of, this function right here. Everybody with me? Now, how do you find this on your own? Where did this come up, and did I just consult my inner oracle, or how did I get that? Right? Well, notice that by these equations being equivalent, another way to say that is, I thought about it as going that way, but you can just think about the equation going the other direction. And notice that what you're doing when you're taking this the other direction is you're taking a y that was just kind of part of the equation, and you're solving for it. Right? So, neat trick. If you want to find the function whose graph is a given curve, then what you're going to do is take the equation that you're given and solve for one of the variables. And in a case like this, if you can, all else being equal, solve for y. Because we typically think of y as a function of x. How are we doing? Why would we want to do such a thing? Why would I want to take a perfectly good equation and think of it as being a graph of something? Well, because we're going to develop a calculus of graphs. Y'all have already seen some of calculus of graphs, right? That's in single variable calculus. So, for example, what's the slope of this line? Slope of this line is, it's the derivative. Be careful. It's the derivative of the function whose graph you're looking at. Right? So if you want to use the calculus of graphs, calculus of graphs, derivatives gives me slopes, that's pretty cool. If you want to use the calculus of graphs, you've got to find a way of taking the thing that you have and in fact viewing it as a graph. Specifically finding the function whose graph you're looking at. And so definitely a useful thing, and that's how you do that. Now, there are more options here. There is a function for which we are looking at a level set. Keep in mind, a level set means we're setting it equal to a constant. What function would I set equal to a constant to give me this equation? And sometimes the fish jump in the boat. It's already written as a function equaling a constant. It was a freebie. I didn't have to solve for anything or rewrite the equation. It's already given as a level set. And so the function whose level set gives me that equation is this function. Now again, why would we want to do that? Who cares about finding a function whose level set is a given line that we happen to be looking at? And the answer is we're going to be developing over the next few weeks a calculus of level sets. And the calculus of level sets is different from the calculus of graphs. And in certain ways, more powerful. It allows us to do certain things that the calculus of graphs isn't really very good at. So being able to rewrite something as a level set, and what function is it whose level set I'm looking at? Very nice trick that opens the door to using the calculus of level sets, which again we will get to. Okay, and then lastly, now again, the grammar is sort of backwards on this, but how would I parameterize this line? What function is it that parameterizes this line? And so this is something we covered a while back, how to parameterize a line, and you may recall that one thing you can do is take a point on the line, 0, 2, and then you can take a vector parallel to the line, and I'm going to subtract these points, and that gives me 3, -2, and a plus tv and all of that. And this algebra right down here, this function parameterizes this line. Again, who cares? What's the point? Well, we're going to have a calculus of parameterizations. And the calculus of parameterizations will give us valuable information about this line that the calculus of level sets doesn't give us, and that the calculus of graphs doesn't give us. Right? So we're going to have all these different connections between algebra and geometry, each one with their own different rules of calculus. What kinds of derivatives tell us what geometric information. And so being able to reliably and accurately infer these functions, all very different from a given line or curve or surface eventually, is going to end up being a really valuable thing. How you doing? Everybody okay with this? Okay. All right. Okay. Moving along. So I feel like I've already kind of talked through this. We're going to have different derivatives of different kinds of functions are going to give you different geometric interpretations. So, okay. All right. Okay, so another neat fact about graphs and level sets and such. Sometimes you might have one written in one form, but you need it written in a different form. So, for example, you might have a surface given to you as being a graph of something. So you're teed up to use the calculus of graphs. But maybe, even though it's given as a graph, the thing that you need to know might be just, but it's perfect for the calculus of level sets. And if it's given to you as a graph, but you wish it was written as a level set so that you can use the calculus of level sets, again, very different from the calculus of graphs, then you need to know how to find what is the corresponding new function. Obviously, a graph and a level set of a given single function are different things, right? But a graph of one function, it's going to turn out, we're going to see here, is a level set of a different function. So here's how this works. Suppose you're taking a graph, and you can see right here that we're looking at a graph because we've got y equals, right? And that is a graph of this function, which you'll notice has n input variables. So you can see the graph of f is described by that equation right there. Okay? Everybody good? Okay, now, the easy part of this argument is to observe that if you take this equation and just kind of subtract one term over to the other side, that gives you this equation, and now, again, that's nothing, hardly anything happened here. I took a term, I subtracted it over to the other side, right? There's no tricky curves with that. But the tricky part is interpreting what this means, and notice that now, having been written in this new form, I am indeed looking at a level set all of a sudden. And I can tell you exactly what we're looking at a level set of. The thing that I have set equal to a constant, in this case 0, is this new function. Right? And you can see exactly what that function is. Here it is. It's y minus f. Very importantly, this is not f. Right? This is a totally different function. This has more variables in it than f does. F has input variables. This expression here, to compute this thing on the left side of this bottom equation here, this thing has n plus 1 variables. I'm going to need to know the values of x1 through xn and y. Right? So it's a function of n plus 1 variables. Okay, so the graph of the function f that I was given, I can reinterpret as a level set of this new function. Let me say that a little bit differently. If a question is stated in such a way that it's teed up to use the calculus of graphs, but if that doesn't give me what I want, the function that I should instead apply the calculus of level sets to is this other function. Now let's see an example of this in action. Here is a function of two variables, and I can talk about the graph of that function. Again, graph, because I have new variable equals 2, value of that function. If I am given this graph, aka that equation, of course it is equivalent to that equation. I barely did anything, right? All I did is subtract everything over to one side of the equation. But having done so, I can now realize this as being a level set. Right? It's a level set of specifically that function. So rather than being stuck with, well, I guess I have to apply the calculus of graphs to this function and do what I can with the calculus of graphs applied to this function. No, I also have the option. I can apply the calculus of level sets to this function and draw different conclusions that might be more useful than what F told me. Yeah?
The G versus zero notation.
Yes. Yeah, this is just a notation that we came up with. So keep in mind when you're taking a level set, you're taking input points, plugging them into a function, and seeing what output comes out. But with the level set construction, you fix the output, and then ask, okay, well, yeah, but what input points give me that output? So you're, instead of normally when you plug into a function, you plug in inputs and out comes an output. We're setting an output and then kind of working backwards, kind of reverse engineering what were the inputs that would have given that to me. And since it moves backwards, that kind of motivates this G inverse notation. It's just a notation. Again, I emphasize G inverse is not a function. G is not invertible. This function here that I call G, definitely not invertible. But the notation is just kind of vaguely suggestive, and it's pretty common. Yeah.
So just trying to understand level sets better.
Yeah.
We're trying to do, let's say, a visualization of that. I'm now going to hesitate to call it a graph because.
Yeah. Thank you.
Yeah. But basically, if you're creating a level, you're creating like an extra axis, and then you would have some, let's say, your original function was like two-dimensional. If you created an extra one, would it be like a surface you would create then? Is that like each level of it?
So one thing that's important is to keep in mind that both of these are the same equation morally, right? So where did the new dimension get created? I would argue that the new dimension got created, we started with a function of two variables, and then by setting it equal to z, now we've got a function of we have an equation involving three variables. So I didn't create anything new when I decided to reinterpret it as this, right? I just basically, rather than interpreting x and y as inputs and z as an output, I just decided to interpret x, y, and z all as inputs. And there is no, I'm not giving any name to the output. There is no, the output is always 0, so why would I give it a name? 0 is perfectly good.
So we're not
yeah.
changing the constants, but we're going to have that equal.
You could. If I wanted to, for whatever reason, and this would perhaps be a little unnatural, but I do have some old exam questions where, just to make sure students understand what level set means, an old exam question was, the graph of this function, right, is the level set h equals 5. What is h? Right, and the idea is you do exactly this, and then you say plus 5 on both sides of the equation, and then z minus x squared minus y squared plus 5 equals 5. And so this is a function which, when you set it equal to 5, is equivalent to the original. So, yeah, sure, you can think of it. There are different level sets you could look at, but in some sense you don't need to. Does that make sense? Yeah. Okay. All right. Okay. Bad news. This is a one-directional convenience. Yes, every graph is a level set. Not every level set is a graph. So an easy counterexample, if you've got a level set, here's one. This is a level set. That's a level set of this function right there, x squared plus y squared. Right? It's a level set. That level set, of course, in this case, we can see is the unit circle. That level set is just not a graph. It just isn't. It's not that we can't figure out how to do it. It's that it isn't. You cannot view this as a graph. Fails the vertical line test for one thing. All graphs have to pass the vertical line test, or the appropriate analog of the, if x is a function of y, then it'd be a horizontal line test. But here, trying to, can I interpret y as a function of x? Nope. Just can't. You cannot solve in the sense of get a unique value. You cannot solve for y because there is not a unique value of y to be found. There are two of them, and so you can't view y as being a function. Okay, so that's the bad news. Don't assume that you can go in. Sometimes you can. Sometimes you can get lucky, but not always. Usually not. Okay, here's a cool argument. Now this is the first of two tools that I'm going to show you for how to understand multivariable equations. Now y'all have a lot of history with understanding equations of two variables. Right? And so, hyperbolas, parabolas, ellipses, that kind of stuff. And then, various variations of them. What if there's three variables? Again, I'm not going to be able to give you tools for answering all such questions. But I can give you certain tools that will, in many cases, allow you to figure out what you're looking at. Okay, so here we go. First tool. Something that's really easy to check. You can eyeball glance at an equation and look and see where the x's and the y's are in the equation. And this comes up surprisingly often, if x and y show up only, exclusively, as part of this expression, the square root of x squared plus y squared, then it turns out there's a really powerful conclusion you can get from this. And that powerful conclusion is your surface is rotationally symmetric around the z-axis. So I really love this observation because it's so easy to check. Eyeball glance. Just look for things like this and make sure that x and y don't appear anywhere else other than as part of this form. And if that happens, again, it's super easy to check that you get this very powerful conclusion. The surface that you're trying to understand is rotationally symmetric around the z-axis. Most surfaces aren't. Knowing that it's rotationally symmetric around the z-axis is going to make it much easier to draw. I'll show you an example in a couple of minutes. So, very powerful conclusion here. Let me show you why it works before we do the example. Think about a point like this. This one right here, that point. And now imagine, if you will, rotating it around the z-axis, and you rotate it around to get this point, which of course, different point. Two totally different points. Different coordinates. Well, at least different x and y coordinates. So, if you plug in these two very different points into a random equation, of course, there's no relationship between, you might have one work and one not. Or you might get both work, or you might get one work and the other one not. Or maybe they both don't. Who knows? There's no connection because they're totally different points. And why would they have any relationship at all? But, notice what I've done here. Even though they're different points, because I've rotated the dark blue point around the z-axis, the distance from the z-axis, same for both of these points. Right? And the z-coordinate is the same for both of these points. So, in the way that they plug into an equation like this, right, where x and y only appear as part of that form being r, after all, right? These 2 points, well, they've got the same value of r. Same value of r, and again, because of one is the rotation of the other, they have the same value of z. So these 2 points, when you're plugging into an equation like this, they either both work or they neither work. They're tied to each other as in terms of how they relate to that equation. Because, again, the only thing that distinguish these points from each other never show up in the equation. So that means that any points that are rotations of each other are either all on the surface or none on the surface, and that means that our surface is rotationally symmetric as desired. So that's the big idea. Now let me give you an alternative point of view on this. Same conclusion, different reasoning. I claim that an equation like this, the cylindrical equation, wouldn't have any thetas in it. And again, let's just kind of think that through. How would you get thetas in a cylindrical equation? Well, x, when you plug in for x, x's are cosine theta. So if you have x's in your equation, you kind of expect some thetas to show up. Ditto y. But the thing is, if those x's and y's are only part of this form, and this form is R, no thetas, right? Then the only x and y's that exist are going to be x's and y's that simply give you R. So there's no way for the thetas to show up at all in the equation. And we've already talked about what you get out of this property here. If a cylindrical equation doesn't have any thetas in it, that means that all the theta cross sections look exactly the same. And so again, conclusion, rotationally symmetric. Okay, all right. So two good arguments that get you to the same conclusion. Let's see an example of this in action. The big idea is that if you have rotational symmetry, then really all you have to do is understand any one of its cross sections, specifically any cross section containing the z-axis. If you understand any one of its cross sections, and if you know it's rotationally symmetric, then you can just take that one cross section and just imagine geometrically rotating it around the z-axis. It will generate your exact surface. Okay, example. As previously promised, let's understand this equation right here. And I previously gave you a hand-waving argument that it's kind of a bowl. Okay, let's argue about why though. Okay, step one, observe x and y appear only in the special form. Now you might quibble and say, hey, where's the square root? Fine, no problem. Let's rewrite this as z is square root of x squared plus y squared, and as desired, x and y appear only in the special form. So, cool. Nice little upshot is if you're missing the square root, don't worry about it. It's fine. Okay, so we have a rotationally symmetric shape here, and therefore I'm going to focus my attention. Oh, this is rotationally symmetric around the z-axis. So now I'm going to focus my attention on any cross-section that contains the z-axis. Now again, I emphasize it can be any cross-section. It could be the it could be the xz plane, the yz plane. If you're feeling kind of crazy, you could pick something like this, some angled plane, whatever, as long as it contains the rotation axis, namely the z-axis. I'm going to stick with the YZ plane here, no particular reason other than, I kind of like the way it looks on the page because I feel like I'm looking right at it. You know, I'm not looking at some angled view of it. I'm just seeing it straight on, head on. Okay, so let's try to understand the cross-section in that plane. By the way, in that plane, notice x is always 0 in that plane. If x is equal to 0, I can plug that into here, and I can see what this turns into. That just turns into z equals y squared, and that is easy. Z equals y squared, that's a parabola, old high school algebra, our old friend. Right? And so that parabola, z equals y squared, looks kind of like that. Okay, so step one. We argue it was rotationally symmetric, and I therefore only need to understand any one cross-section. Step two, I have identified one of its cross-sections. Step three, we're just going to rotate around the z-axis. And when you rotate this purple parabola here, rotate it around the z-axis, well, I think it's pretty easy to believe it gets you the bowl that I claimed it was. What do you think? Everybody buy it? Okay. This is a really great trick. It's useful in a lot of circumstances. You'd be surprised how often it happens that the thing that you're trying to understand has this feature that x and y appear only in this special form. Okay, another example. Before I get ahead of myself, terminology. This is called a paraboloid. That's just terminology. I think the terminology is pretty satisfying. You can see the root parabola in there. The oid part is just kind of a conventional. That kind of says, yeah, but it's a surface instead of a curve. So paraboloid. Okay. All right. Okay. Next example. What is this oddball right here? Got an equation, 3 variables. Again, but it's not familiar. It's not something we've seen before, right? So notice step 1, x and y appear only in the special form. So this is rotationally symmetric around the z-axis. And again, we're in business, and all we have to do is understand a cross-section. Step 2, pick any plane that contains the rotation axis, namely the z-axis. Just to show that I'm going to use the xz plane this time instead of the yz plane. Again, doesn't matter. Whatever. It's all good. Let's just mix it up. See what happens. Well, now, y is equal to 0 in that plane. I can plug in y equals 0 into there. This becomes that thing, x squared minus z squared equals to 1. Again, only 2 variables at this point. Old high school algebra. And by the way, I know it's been a while, and hyperbolas are confusing. And which way does it go? And does it go this way or does it go the other way? And it's easy to get that backwards. Dust off all your old high school algebra notes and make sure that you're comfortable and proficient and reliable with getting this right. It is surprisingly important to get that part right. And that parabola goes this way. Hyperbola goes this way. And okay, so again, step 1, we observed the rotational symmetry. Step 2, we understood a cross-section. Step 3, we rotate around the z-axis. Right? What happens when you take that purple hyperbola and rotate around the z-axis, and I appeal to your geometric intuition, we get something kind of like this. Everybody with me? Yes.
So we can still make the assumption that with the x squared plus y squared, even though there's like a constant there.
Say it one more time. I'm sorry.
So there's the constant one.
Yeah.
Does it affect the fact that we have an x squared and a y?
Oh yeah, no, that's not a problem at all. The point is, if you look for x's and y's in this equation, the only x's and y's are right here. And elsewhere in the equation, you're allowed to have all the z's you want in whatever ugly form might be there. We don't really care about that. And constants, yeah, sure, no problem. The key point is that x and y appear only in the special form. Is that all right? Yeah. Yes?
Are we going to have to make the drawings more specific, or would it just be like sketches to this to get the general shape?
I mean, probably something just along these lines. I might ask you to label certain, maybe just a little bit, but that's not the kind of thing I'm usually going to get uptight about. I'll try to, on any exam or anything, I'll try to make it unambiguous. What exactly I want to see. And by the way, broad point, if on an exam you're ever not sure, do I need to label this point or that point, or what other additional, if something about the phrasing of the question does kind of leave open interpretation, you're very welcome to come up and ask during the exam. And I encourage you to clarify rather than assume and end up having assumed wrong. Yeah. Okay. Now, the examples that I've showed you here all have rotational symmetry around the z-axis. But there are similar arguments that you can make for symmetries, rotational symmetries around the other axes. I'm going to leave those arguments for y'all to think through on your own. It's going to look a lot like this one. It's going to look a lot like this. And just think about, though, instead of x squared plus y squared, what if it was y squared plus z squared? That would be distance away from what axis? And picture and argument, blah, 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 and you'll get a result about rotational symmetry around the appropriate axis. Now, you could probably guess, just from sort of the pattern, that if it's y and z that appear only in the form of square root of y squared plus z squared, you would probably guess that would mean rotational symmetry around the x-axis. And that is correct. And likewise, if it's square root of x squared plus z squared, and only x and z appear only as part of that form, then that's rotationally symmetric around the y-axis. So exactly what you would think, but again, I think it's a healthy exercise. Try to reproduce this argument, make the analogous picture, and persuade yourself that these rotational symmetry arguments work as you would kind of guess that they would. And knowing that they do, here's an application. Let's try to understand this surface. Okay, x and y, no luck. That minus sign messes it all up. This is not rotationally symmetric around the z-axis. It just isn't. The minus sign matters. Close is not close enough. And so we got nothing. No z-axis symmetries that we can argue. Okay, but you rewrite it like this, and you notice that y and z appear only in the special form. So this thing is rotationally symmetric around the x-axis. And so I'm going to draw, there we go, the x-axis right there. Okay, how are we doing? Everybody okay? Okay, rotational symmetry around the x-axis. Fine, I can pick any plane that I want that contains the x-axis. So I've got options. I can look at this plane, or I could look at that plane, or I could, again, if I wanted to just, for whatever reason, make my life harder, I could look at an angled plane like that. You got a lot of options. Any plane at all that contains the rotation axis. In this case, I'm going to do the XY plane because it's the only plane I haven't used yet, and I just kind of want to mix it around. Right? So this plane, what's going on in that plane? Well, in that plane, z is equal to 0. Right? Plug in z equals 0, and our equation turns into this. Which again, familiar, hyperbola. Dust off those old notes. Make sure that you're good with, hyperbolas and stuff. And that hyperbola is like this, which ends up making the picture look like a basketball court, oddly. So that is the cross-section in the XY plane. We have rotational symmetry around the x-axis, so I can just rotate that around the x-axis. And here again, you have to use some geometric intuition. These kind of two curves, when they rotate around the x-axis, they don't rotate into each other like the last example. They kind of rotate parallel to each other, and the resulting rotated picture is you get these two kind of separate things. I don't know what y'all see in this picture. To me, what I see in looking at this is it looks like a contact lens to me. And so this picture is what I like to call the staring contest. Right? It's two eyeballs that are just kind of pointed right at each other. Anyway, the more common standard name for this is hyperboloid of two sheets, because it's a rotation, literally a rotation of a hyperbola. Yes?
Could you mind explaining why it's two sheets and the other one was one sheet?
It just, hyperbolas are weird, and when you rotate this hyperbola, for example, when you rotate it that way, those two pieces kind of, like I say, they kind of rotate parallel to each other, not into each other. And this is just different. I mean, this one, when you're rotating that way, this piece kind of rotates right into the other piece. So
in the example below, had we rotated it against a different axis, we could have gotten a one-sheet hyperbola.
Well, you can't. You can't, because this is fundamentally a two-sheeted hyperbola. That's just what it is,
Okay.
right? So yeah, so the pictures that we draw are not consequences of the choices that we make and how to understand them. They are consequences of the equation, period. And how we choose to understand it is just going to be, what's convenient for us. But there is only one answer.
So even if we would have let y equal to 0, we would have gotten the exact same answer.
Correct. Yeah, that's right. If you had chosen instead of this plane, if you had chosen this plane, then you would have gotten this hyperbola, and rotating that hyperbola again around the x-axis, you get exactly the same picture. Yep. Yep. Yes.
Could we have tried to do it with a vector solution around a different axis?
You can try, but it's just not going to work. You're going to be dead in the water at the very first step. So, for example, let's talk about trying to rotate this around the z-axis. Right? If you wanted to do a z-axis rotation, you would need for it to have rotational symmetry around the z-axis, which means x and y would have to appear only as part of the special form, and it just doesn't. Right? X squared minus y squared is not, something that you can algebraically create out of just x squared plus y squared. It's just a different thing. Does that make sense? Yeah. Cool. Good stuff. Okay, so various different kind of results that we can get there. And I'm going to move it along now to, what I call deformations. So sometimes, as in this situation here, let's say I want to understand this equation. And there's certain things I could do there. I could make a rotation argument here. To be fair, I could. Right? But let's say I didn't want to. Let me point out that this equation looks an awful lot like this equation, which I already understand. This just says rho equals 13. It's a sphere. Boom, done. Right? Easy observation. This equation we love because it's immediate and I know exactly what it is. So, when you have two equations that kind of look like each other, they're not exactly the same, but they kind of look like each other, what would be nice is if we had some way of understanding what happens when you tweak an equation like I did here. Notice here, I replaced all my z's with 2z. Every z in the left equation, I erased it, and in its place I put 2z. Wouldn't it be nice if I could understand what happens geometrically when I do that move algebraically? Right? And it turns out this is actually pretty easy to understand, as it turns out. Here's the I'm going to give you just kind of the intuitive version of it. I'm not going to be rigorous about this. But this point right here, 3, 4, 12, you plug this in and this equation works, but this equation obviously doesn't. Clearly the numbers are wrong. That extra factor of 2 just completely screws things up. But the clever move is to notice that if I were to put a 6 there instead of a 12, that 6, when I plug in for this z, the first thing that happens to that 6 is it gets multiplied by 2 and becomes a 12, which is the thing that I was squaring that made it all work over here anyway. So putting a 6 here instead of a 12 basically returns me to the same arithmetic that worked in the previous equation, if you will. Everybody kind of see what happened there? So in some sense, I'm going to choose to think of it this way anyway, the action of replacing all the z's, get this thing done. The action of replacing every z with 2z, what that does is it takes the actual z coordinates and divides them by 2. Right? What had been a 12 turns into a 6. It's like we are therefore squishing the surface by a factor of 2 in the z direction. Is that cool? So this is an example of a general point. In some sense, when you do something to the variables in an equation, here I kind of, if you will, multiplied the z variable by 2. The exact opposite happens geometrically. We're squishing in the z direction by a factor of 2 as a result. So this, again, pretty general fact. What you do to the variable in an equation, the opposite happens to the surface. And I just ran out of time, so that's kind of perfect. We will pick up here next time. Hope you all had a good weekend. Good to see you again. And again, reminder, if you came in after I did the attendance, make sure that I get you marked down. I'll call names again in just a second.